Bismillahirrahmanirrahim. Welcome to the online course of the numerical solution of partial differential equations. We have started the numerical solution of parabolic partial differential equations and discussed some explicit and implicit schemes for the solution of parabolic equations. We did some problems. In today's lecture, we will discuss about the local truncation error and stability of the explicit scheme by matrix method. We consider the heat equation defined in N1, where N1 ut represents partial derivative with respect to t and uxx represents twice partial derivative with respect to x. Using forward difference for ut and central difference for uxx, we get equation 2. Equation 2 is known as the difference equation. You can see in equation 2 Fij of u. This is a kind of notation which play a crucial role in coming part of the lecture. As discussed in previous slide, let Fij of u equal to 0 represent the difference equation approximating the partial differential equation defined in N1 at the ith mesh point with exact solution u. If u is replaced by u at the mesh point of the difference equation, where u is the exact solution of the partial differential equation, the value of Fij of u is called the local truncation error, denoted by Tij at the mesh point ij. Fij of u clearly measure the amount by which the exact solution values of the partial differential equation at the mesh point of the difference equation do not satisfy the difference equation at the mesh point. It is to be noted that small u represent the solution of the difference equation, while capital U represents the solution of partial differential equation defined in N1. Initially, we consider the Fredholm integral equation of second kind defined in N1. In this method, we replace the unknown function under the integral sign, which is basically u of t, and the Fredholm integral equation of second kind by any selective real valued function u0 of x, where x lies between a and b. Accordingly, the first approximation u1 of x of the solution u of x is defined by 2. What we are doing here, we just initially select any real valued function u0 of x, and this will be our initial approximation. And then we use this initial approximation to define the u1 approximation, which is the first approximation, and this approximation is defined in 2. The second approximation u2 of x of the solution u of x can be obtained by replacing u0 of x in equation 2 by the obtained approximation u1 of x. Hence, we find. Now I am going to show you that how to calculate the order of local truncation error for a numerical scheme. For this, we consider the following example. Calculate the order of the local truncation error of the classical explicit difference approximation to heat equation at the mesh point ihjk or ij. To obtain the order of the local truncation error for classical explicit finite difference scheme, what we do, again we consider the difference equation Fij of u as discussed earlier. Now from this difference equation, we can obtain the local truncation error Tij by replacing small u with capital U in the difference equation. Now, in truncation error, you can see we have 4 terms: uij plus 1, uij, ui minus 1j, and ui plus 1j. In these 4 terms, we can use Taylor series expansion for 3 terms, namely uij plus 1, ui minus 1j, and ui plus 1j. By using Taylor expansion, we have ui plus 1j is equal to u at the point I plus 1 into h jk, and this will be equal to uxi plus h and tj. Since we have used alternative notation that if xi is any point, then xi plus h will be equal to I plus 1 into h, And similarly, if we have two variable functions, then uxi plus htj will be equal to ui plus 1 into h and jk, and this will be equal to uij plus h partial derivative of u with respect to x at the point ij, and plus 1 by 2 h square and double partial derivative of u with respect to x at the point ij, and plus 1 by 6 h cube third order partial derivative of u with respect to x at the point ij, and so on. Similarly, we can find out ui minus 1j and uij plus 1. Now, using ui plus 1j, ui minus 1j and uij plus 1 and the truncation error, the resultant is tij. Since u is the solution of the partial differential equation defined in 1, so partial u by partial t minus partial square u or partial x square at the point ij will be equals to 0. Therefore, the principal part, which means that those terms having least powers of k and h, which contributing in the local truncation error, is given by 1 by 2k partial square u or partial t square minus 1 by 12 h square partial 4u or partial x4 at the point ij. Hence, the local truncation error tij can be written as order of k plus order of h square, because the least power of k is 1 and the least power of h is 2. Now we are going to discuss the stability of classical finite difference explicit scheme. First, we discussed the stability by matrix method. As you saw in the previous slide, that truncation error in classical explicit scheme is of order k plus h square. Explicit scheme works in some cases, while in some cases this gives drastic results. To explain the difficulty, we need to look at the stability analysis of the explicit method. Since the initial condition is defined by u at xi0 is equal to f of xi, where I starting from 1 reaches up to m minus 1. Remember, we are taking only the internal points because we considered that the solution at the boundaries are 0. Suppose that an error E0 is equal to E10, E20 up to EM minus 10 transpose is met, and representing the initial data, U0 is equal to f of x1, f of x2 and up to f of xm minus 1 transpose. Or in any particular step, the choice of the initial step is simply for convenience. So this error E0 and U0 mean that if we are computing the initial condition at discrete points, so corresponding to f of x1 there should be error E10, corresponding to f of x2 there should be error E20, and up to so on corresponding to f of xm minus 10 there should be error em minus 10. Now, since in matrix form the explicit scheme is given by uj plus 1 is equal to auj, where A is the tridiagonal matrix of dimension m minus 1 cross m minus 1. In previous slide, we used uj plus 1 is equal to auj. For j is equal to 0, we have u1 is equal to au0, where u0 represents the initial data at discrete points. Also, we considered in previous slide that let's say an error E0 exists in the initial data. Therefore, an error E0 will propagates to U1, and then U1 will be equal to A into U0 plus E0, and this will be equal to AU0 plus AE0. And next step, this error will be A square E0, and this process continuous. At the nth time step, the error in UN due to E0 will be AN E0. The method will be stable when these errors do not grow as n increases. These errors mean a is 0 will not be greater than e0, then a square e0 will not be greater than e0, and so on. But this is true if and only if for any initial vector e0 we have a power n e0 norm is less than or equal to e0. Hence, we must have a n norm less than or equal to 1, a condition by theorem 7.15 on page 446 of Burden and Fair requires that spectral radius of a power n, and this will be equal to spectral radius of a whole power n, is less than or equal to 1. Thus, explicit scheme is therefore stable only if spectral radius of A is less than or equals to 1, because in the previous expression spectral radius whole raised to the power n. So if spectral radius of A itself less than 1, then whole power of that less than value of 1 will be less than 1. Since A is tridiagonal matrix and its eigenvalues or mu I is equal to 1 minus 4 lambda sine I pi by 2m whole raised to the power 2, where I starting from 1 reaches up to m minus 1. Here we have used a general result recording the eigenvalues of the tridiagonal matrix of m minus 1 cross m minus 1 dimension. So the condition for stability reduces to mu I absolute values is less than or equal to 1. Here we use another inequality that if x mod less than or equal to a, then minus a will be less than or equal to x will be less than or equal to a. That's why above inequality reduces to minus 1 less than or equal to mu I is less than or equal to 1. So subtracting 1 in this inequality, we have minus 2 less than or equal to minus 4 lambda, and to sine I pi by 2m whole raised to the power 2 is less than or equal to 0. Multiplying the above inequality with minus 1, the order of inequality will reverse, that is 0 will be less than or equal to 4 lambda sine I pi by 2m whole raised to the power 2 will be less than or equal to 2. Since right hand side of the inequality is obvious, that is 4 lambda sine I pi by 2m whole square is greater than or equals to 0. Therefore 4 lambda sine I pi by 2m whole square is less than or equal to 2, and maximum value of the sine function is 1, so that's why 4 lambda will be less than or equal to 2, and this implies that lambda will be less than or equal to 1 by 2. Hence the scheme will be stable if lambda is less than or equal to 1 by 2. Remember, I told you in example sections, and we practiced this, that if lambda is less than or equal to 1 by 2, then this scheme works. If lambda exceeds 1 by 2, then this gives us drastic results. Hence the stability condition is that lambda should be less than or equal to 1 by 2.